This video will focus on three terms: vapor pressure, evaporation, and boiling, with a learning target of I can explain how vapor pressure relates to evaporation and to boiling. So in this case, we're focusing on liquids. Liquids have less energy than gases, and they have more energy than solids. They're your state of matter right in the middle, right? Liquid molecules are attracted to one another through their intermolecular forces. That's what's keeping them in a liquid phase. Okay? They slide past one another. They're not as rigidly held in their intermolecular forces like solids are, but they have forces, so they don't generally escape into a gaseous state of matter. Some will escape, and we're going to use that to help us understand evaporation and boiling, but most are held together through intermolecular forces. So let's talk about evaporation. People tend to take for granted the fact that if there's a puddle outside on a warmish day, even, just an average day, 40, 50, that puddle will eventually evaporate. You know that the process of changing from a liquid to a gas is called boiling, and yet at no point does that puddle boil, yet the water all becomes gas. What's going on here? Okay. That process, evaporation or vaporization, what's happening is that the high-end particles within that liquid are able to escape into a gas. So again, if we revisit our Maxwell distribution with the understanding that temperature is an average of the kinetic energy in the system, that means some particles will always be hotter than the average, which means those hot particles, or those particles that are moving fast, may able to break away and overcome the intermolecular attraction of their state of matter. Okay? The average kinetic energy, of course, is below the boiling point. Your liquid's not boiling, but some particles are hot enough or moving fast enough that they can break their intermolecular forces and move into a gaseous state. If we want to increase our rate of evaporation, obviously we can shift our average kinetic energy higher. What that's going to do is just move more particles into the range where they may be hot enough to escape into the gaseous form. Now, oftentimes evaporation is thought of as a cooling process. Okay, think about how you sweat. When you sweat, the whole point of sweat is that the water is going to evaporate off of your skin. And when it evaporates off of your skin, it takes some of the heat with it. What do I mean by that? Well, if your hottest particles are constantly leaving, right, that only leaves the cooler ones behind. That is going to be an overall cooling process. You're going to have only the cooler ones left. Now, your Maxwell distribution constantly reshifts itself because your average stays pretty constant, especially with a constant heat source like the sun or just the surroundings. But evaporation can be thought of as a cooling process because it takes some of the hottest particles and moves it into a different state of matter. Now, because of evaporation and that vaporization, every single liquid has something called vapor pressure. And that's that pressure created from the gas particles moving up off the liquid. Remember, pressure is just force per area of molecules striking things. So the fact that the vapor pressure is molecules moving off the liquid, we are applying a pressure up off of our liquids onto essentially the atmospheric pressure. Okay? That vapor pressure is temperature and substance dependent. What do I mean by that? Well, we already said if you increase your temperature, you're going to increase your rate of evaporation because you'll have more hot particles able to escape. So a hotter substance will frequently have a higher vaporization or vapor pressure, right? And then it's substance dependent. And by that, we mean that all substances have their own boiling points, and all substances have their own intermolecular forces. Okay, remember, it was the ones with a higher intermolecular force that's going to be harder to escape from. Okay, it's a measure of volatility. And way back, we did an intermolecular force lab where we looked at volatility, and the ones that were more volatile had a weaker intermolecular force. Okay, so when you're trying to evaporate, you're really trying to do two things. You're trying to overcome the intermolecular forces to escape to the gaseous phase, and you're basically creating a pressure as you do that. And there's a reference to temperature because as you get hotter, you're more likely to overcome that intermolecular force. Okay, so it's temperature dependent because the hotter it is, the more likely you are to overcome it. but then it's also how strong is that intermolecular force in the first place. Because if it's a weak one, you may be able to escape at a lower temperature. So you will find that in an open system, like outside, again, in a puddle, your evaporation, in terms of your particles coming up, will be such that that puddle could eventually disappear. If you have something in a closed container, what's going to happen is you still have vapor pressure, you still have things evaporating, but because of the way the system is set up, if the particles can't escape, they're going to recondense too, because they're all in one environment. So we can have this system of evaporation and condensation kind of going, where you have particles flowing in both directions. So what's the difference between evaporation and boiling then when we look at it? Well, what's happening when you boil something is that rather than just some of your particles being able to escape the intermolecular forces and become gaseous, the majority of the molecules have enough energy to overcome the intermolecular force and become a gas. So basically, you've taken that Maxwell distribution for boiling and shifted it so that your peak is at that temperature where where at least half of your particles are hot enough to escape. The other thing that has to happen for boiling is in order to overcome that intermolecular force, you actually have to create enough vapor pressure coming off the liquid to overcome the pressure being exerted down on the liquid. When you just have a couple molecules coming off every once in a while, they can usually overcome the pressure. But for boiling, you actually have enough pressure on the system and enough molecules trying to come off that you need to have a vapor pressure being exerted up that's equal to the atmospheric pressure down. What that means then is that the pressure on the system actually affects the boiling point. And you've heard this before. You've heard and seen on cooking things that you need to cook longer or shorter depending on what your altitude is. And the reason is that you boil at a different temperature. Right? You may boil at a hotter or a cooler temperature, which means cooking times would vary because the water isn't as hot or is more hot. Okay? This graph is something we'll spend time on in class, but what you have here is 3 different substances, and you can see each one has a line. And what that line is the corresponds to the temperature and pressure at which a substance would have enough pressure to overcome the pressure down, essentially. So that line that's up on the top of the screen right now corresponds to the boiling points of these 3 substances at atmospheric pressure at 1 atm, and the temperature and the pressure correspond to the temperatures that they boil at. Now, if you start decreasing the pressure, meaning moving this line down the graph, you can see how your temperature that it boils at will be affected. You'll be able to boil at a lower temp, and actually do demos of this in class tomorrow. If you feel like you might want more on this topic or would like to look at a different way, your book, Chapter 13, Section 2, deals with all of these terms also. And it's just a few page read if you feel like reading about it might help you in your comprehension. So evaporation, boiling, and vapor pressure. Evaporation is the process by which the hot particles escape from the liquid phase into the gas phase. They need to overcome the intermolecular forces in order to do that. And as they do that, they create a vapor pressure at the top of a substance. To get to boiling then is when we have the average temperature hot enough for the majority of particles to be able to escape the intermolecular forces, and they're actually able to create a pressure up that exceeds the atmospheric pressure down on the liquid so that the particles can escape. Okay? So vapor pressure is created by evaporation, and vapor pressure has to equal or exceed atmospheric pressure for boiling to occur. Okay? Go ahead and do the form. Those are your 3 terms. Have a nice night.